Our topic today is large diameter pipelines. Today's topic will provide an overview of the design, construction, inspection, and rehab of large diameter water transmission pipelines. Our presenters today are Shah Rahman and Dennis Atwood. Shah is KCI's water wastewater practice leader for North Texas and Dallas. And Dennis is a senior project manager and program manager at our Houston office. With that, I'll turn it over to Shah.
Thank you, Mehmet. So in today's presentation, we're going to look specifically at large diameter pipe, water pipe, in particular steel pipe and PCCP, prestressed concrete cylinder pipe. So before we get to the meat of the presentation, let's kind of get an understanding of America's drinking water infrastructure. So there are over 150,000 potable water systems in the United States, serving a population of over 330 million people through more than 2 million miles of water distribution and transmission pipelines. Let's take a survey here to see which state has the highest number of water systems and which state has the lowest. All right. So we're way off on the most water systems. And we're sort of, okay, we're actually right on the which state has the fewest. So that the answer there is Hawaii. I believe they have only 34. And the highest is by far Wisconsin and not California. And everybody got that wrong. All right. So let's move on to our next slide. Okay, much of the buried pipe infrastructures are now between 75 to 100 years old, essentially surpassing their design lives. And as a result, 6 billion gallons of treated water are lost every day through leaks and an average of 240,000 water main breaks per year. Assuming that every pipe would eventually need to be replaced, the AWWA, American Water Works Association, estimates an associated cost of $1 trillion. ASCE's infrastructure report card gave drinking water systems an unflattering D grade in their 2017 survey. The EPA, in its 2015 sixth report to Congress on drinking water infrastructure needs, states that $472.6 billion is needed over the next 20 years, with 66% of this amount in the distribution and transmission category, that is water pipes. Wow. In comparison, water treatment, for example, needs only 18% of the $472.6 billion. In another study that looks at capital spending, between 2018 and 2027, CapEx is forecast to be over $300 billion in the United States. Two of the largest spenders are going to be California at $44 billion and Texas at $33 billion. There are two main types of pipes used in water utilities, in a water utility system, and they are transmission pipelines and distribution pipes. Transmission lines carry large quantities of water from a source of supply to a treatment plant or from a treatment plant to the distribution system. Transmission lines generally range in sizes of 16 to 24 inch to as high as 144 inches, 12 feet in diameter. In some systems in the Western United States, there are pipes as large as 256 inches or 21 feet diameter. Transmission pipes generally run in straight lines from point to point, have few side connections, and are not tapped for customer service. Distribution mains, on the other hand, are the smaller pipes that carry water from the transmission system and distribute it to homes, businesses, and all other parts of the community. These diameters range from 4 to 12 inches typically In some larger systems, you may find distribution lines as large as 16 or sometimes even 24 inches. Distribution lines typically have many side connections, and tapping is done frequently to provide water to customers. So again, in today's presentation, our focus will be mainly on large diameter transmission pipe design, construction, and maintenance. Large diameter transmission lines that are in service today include primarily welded or riveted steel pipe. The riveted stuff comes from pre-World War II. Reinforced concrete and concrete cylinder type pipe, such as prestressed concrete cylinder pipe, and cast iron and ductile iron pipe. Iron pipes are typically no larger than 64 inches, while steel and concrete pressure pipes are up to 144 inches, and of course larger in some cases. Steel pipe, that is riveted steel pipe, was first installed in the United States in 1858, and prestressed concrete cylinder pipe was first made during World War II in 1942. This picture shows new and old technology from the 1940s. That is a welded steel pipe, which is the one on the left-hand side, and a riveted steel pipe on the right-hand side, carrying water across the San Francisco Bay into the city of San Francisco. Welded steel pipe used for water transmission is also called spirally welded steel pipe. As shown in the top left drawing, steel coils manufactured to the thickness of the pipe, accurate to 3 decimal places, is helically wound into cylinders, while both the inside and outside seams undergo fully submerged arc welding. These cylinders are then typically cut to 50-foot lengths, hydro-tested, and then ends are treated per the type of joint specified for the project, and coatings and linings are applied for corrosion protection. The final products are relatively light compared to concrete pipes of the same diameter. The other type of steel pipe shown on the bottom left drawing is called rolled and welded steel pipe. Casing pipes are typically made as rolled and welded steel pipes. Finally, prestressed concrete cylinder pipe. During World War II, PCCP was the result of our efforts to minimize the use of steel in high pressure, large diameter water pipes, since steel was needed for the war effort. Line cylinder pipe was made in 1942, while embedded cylinder pipe was made in 1953. The steel cylinders used in PCCP are first hydro-tested, just like with steel pipe, after which joint rings are welded to the cylinders. In embedded PCCP, the steel cylinder, as shown in this cross-section, is cast within a concrete core. After curing, hard-drawn steel wire is helically wrapped around the exterior of the cylinder. This results in producing a predetermined compression of the concrete and steel core. The wire is then covered with cement slurry and dense mortar coating for corrosion protection. Line PCCP ranges in diameter of 16 inch to 60 inches, and embedded PCCP range in diameters of 24 to 144 inches. It's estimated that between 1942 and 2006, some 19,000 miles of PCCP were manufactured and installed in the United States. So that should give you a little bit of background on the primarily the 2 types of materials that we're going to be talking about throughout this presentation. With that, I will pass the presentation now over to my colleague, Dennis Atwood.
Thank you, Shaw. So I've been involved in a lot of conversations where we talk about large diameter pipe, and inevitably someone makes the remark that it's different. And so I wanted to kind of try to see if we can focus a little bit about, what is really so different about large diameter pipelines. And so I've kind of taken 5 areas, which I think kind of talks about some of the issues that we have and some of the things that we need to consider when dealing with large diameter pipelines. The first thing I'll be talking about is a selection of pipeline alignments. Then we'll discuss risks just in a small amount, types of large diameter pipelines, and then large diameter valves that go with large diameter pipelines, and of course, construction, inspection, and testing for the large diameter pipelines. Okay, so the first thing, selecting pipeline alignments. Now, what are some of the challenges that we have? The importance of selecting the best pipeline alignment cannot be overstated. Choosing the right alignment can save millions of dollars in construction and land acquisition costs, not to mention the disruption to the public. Now, cities are continuing growing and need water to be able to accommodate this growth. Most cities' existing water sources are fixed, and developing new sources is usually not an option. So it becomes necessary to bring water from the source to where it's needed. So the question arises, how do you get from here to there with a transmission main? Okay, next slide, please. Now, traditionally, we've relied on our existing street infrastructure for pipeline corridors, but as more and more development has occurred, our streets have become congested with utilities. You may be able to snake small utilities or water lines through these congested streets, but when it comes to large diameter pipelines, that's another matter. Next. Large diameter pipelines have large footprints and will take a large portion of the street during construction. Installing a large diameter pipeline will also use considerable real estate and make it difficult to accommodate other utilities in the future. So transmission lines usually span great distances in order to bring water to growing areas. As cities begin to sprawl, all the new growth seems to be on the peripheral, whereas a lot of the water sources are more towards the center or one end of the city, as that is how the city grew. Just to give an example of how large some of these transmission lines can be or how long they can span, I'm currently working on a project in the city of Houston, which is 17 miles in length. And the longest one I've worked on, it was over 30 miles. So you have considerable real estate to cover that you need to consider how you're going to go there. Okay, next. Okay, traditionally, before the days of computing and we had access to GIS, what we used to do is take a map and determine 3 to 5 possible alignments. Each alignment would then have to be vetted for feasibility. A set of criteria was developed by which to evaluate the alignment. Each alignment was evaluated against that criteria, and the evaluation results were input into a matrix for comparison. Based on the methodology, the preferred alignment was based upon the results of the comparison. This method, however, always left you wondering if you had indeed captured the best alignment. With projects costing in the hundreds of millions of dollars, a slight variation in alignment could save the project several millions of dollars and have other unknown benefits. Next slide, please. So with the advent of computers and GIS, this has opened up a whole new avenue of analytical methods by which we can use to determine where our best alignments can be. And we do this every day in our day-to-day lives where we want to get from one point to another while driving. So we open Google Maps, we enter in a destination and an origin, and presto, Google Maps gives us the best route based on either the fastest route, the shortest route, or the least congested route, depending on what input parameters we gave it. Next slide. But what if someone doesn't like to use freeways or wants to avoid the tollways? You can change the input criteria and the program gives you a new alignment, which is totally different from the previous alignment that it had selected. It's not the fact this route would not be the fastest route or the shortest route or perhaps the least congested route, but it's the most desirable route to the end user. Okay, next slide, please. Okay, we can use a similar method when trying to determine how to fit a large diameter transmission line through a highly urbanized area. We want to be able to do the best route, and as I pointed out, what is important to one owner may not be as important to another owner. So the beauty of this method is the ability to customize it to the specific wants and desires of the owners or the operating utility. Some of the parameters that we will look for is the length. Now, the length, of course, is the determining factor for the cost and also the time to construct. But where we go might determine, how the businesses are disrupted, how much disruption we're going to have to traffic. Are we going to be disturbing residences? Are there specific areas in the area that we need to avoid that may have contamination or something else? Large utilities that need to be crossed. Freeways and arterial crossings are always challenging. Environmentally sensitive areas such as wetlands. Soil conditions determine what kind of ease or difficulty we may have in construction for the hardness of excavating and the water that has to be dealt with, and whatever other criteria that might be important to the owner. So we established this criteria, but take it one step further. We then weight the criteria because not all of this criteria is equally important to the owner. So by putting weighting factors, we can bring the most important ones to the top and the least important to the bottom. Okay, next. Okay, so what we do then is develop a grid or a network of links. The network that links the delivery point to the from the source to the delivery point is developed, and then each segment is individually evaluated against the criteria that was assigned, and then we assign values based on that criteria. Then the values are added together to each assigned link to become an aggregate score, and then the higher the score, the least desirable the link. Okay, next. Then using an analytical program such as Network Analyst, the program will determine the combination of links that combines together to connect the start to the finish that has the lowest combined value. Now, Network Analyst is just one example of a program. It's a standard software program that you can purchase, and it works within ArcGIS to do this. But if you want something a little more customizable, there are a number of programs out there. We used, in one particular case, we had a graduate PhD student who was able to develop an algorithm that worked within GIS, and it would actually generate 100 different alignments that could be sorted from the lowest score to the highest score. And so a lot of entities still like to compare alignments. And so you can take the top 10 or the top 5, whatever it is you want, and do an individual analysis. And also the beauty of this this type of program is it'll accommodate any kind of showstopper. So if you need to reroute your alignment, you can. Okay, next. So as I said, the lowest combined value is the best or optimum route that meets the criteria. The analytical method will also allow you to estimate the probable cost, since cost was one of the factors that is input into that, and then it gives you its total length. And then the other thing is the estimated time to complete. So when doing your preliminary analysis and the planning effort, these are some of the valuable parameters that it generates that you don't have to recalculate or redo. Okay, next. Now, as you can imagine, this is a pretty labor-intensive methodology, particularly with these long links. There could be, hundreds, if not thousands, of links that need to be evaluated, and so it can take some considerable time. But the beauty of it, it does, for a planning level effort, it gives pretty accurate results, and so you can work with it fairly well. If you don't want to spend quite that much time on it, you can use other products such as the Geospatial Analysis. Now, this Geospatial Analysis has similar criteria developed and are entered into GIS colored layers or three-dimensional layers whichever the case may be. The darker the color, the least desirable the area, or in the case of a three-dimensional area, the thicker the layer, the least desirable the area. Layers are then overlaid one to another, and then the lighter the area that is connecting the start point to the end point is your most desirable. The beauty about using three-dimensional areas is it almost creates a topographic map that would be similar to where a river might run. And so you can easily identify the area of least resistance, which is your most optimum corridor. Okay, next slide. Okay, let's move on and talk a little bit about risks. Now, there are many risks that you can imagine to a project such as this nature. We're only going to talk about a couple of them today. But normally risks are captured in a risk register, and risk registers may include, 100 to, several hundred identifiable risks depending on the nature of the project. Okay, next slide. Okay, one of the greatest risks that we face that's kind of unique to large diameter pipelines is hydraulic transients or water hammers. There's been many documented cases of catastrophic pipe failure due to a hydraulic transient within the pipeline. Although, water hammers or hydraulic transients are in smaller diameter pipelines, they're usually not of the magnitude, and there's been little cases of pipe failures. Usually a factor of safety is already built into most smaller pipelines that accommodate these. But when we get to large diameter transmission lines that move high quantities of water, the surges that can be created from a hydraulic transient can produce tremendous pressures, both positive and negative, as you can see from the failure modes of these pipes. Okay, next. Okay, the primary way to be able to mitigate this risk is to use a surge analysis program to model the pipeline and predict the surge pressures that will be in the pipe and that the pipe could experience during a transient. The pipeline is then designed to be able to withstand the initial pressure, which can be both positive and negative, as we saw from the previous picture. Other mitigating measures can also be incorporated. Just as an example, we could add a surge tank to relieve that pressure, or to prevent from creating hydraulic transients in the first place, include pump ramping down protocols. Sudden pump shutoffs are one of the largest causes of surge analysis, or if a valve is closed a little too quickly, it could be another cause. So a lot of our operating protocols can be steered to prevent surges from happening. Okay, next slide. Okay, conflicts with utilities, probably the number one risk that we face in construction today. Probably the largest source of change orders in a project is due to conflicts with existing utilities. Now, as I mentioned, large diameter pipelines have very large footprints, and so if there's a rogue utility out there, it's highly likely that you're going to find it during construction. This example of a project on the left is an open faced tunneling operation, which fortunately it was open faced, and they were able to detect a 12-inch water line, which was neither marked on the surface nor shown on the plans within the tunnel before it was struck. This was actually a high hand mining operation, which is one of the safer modes. Had this been a closed face where the cutter had cut into it, it could have flooded out the tunnel with workers, and there could have caused a precarious situation. So not only are they costly, in this case, the tunneling operation was down for about a week and a half while they relocated the line. So there was a financial cost there associated with standby, as well as a delay cost. But had that water been ruptured with men in the tunnel, it could also be a life-threatening situation as well. So, conflict with utilities is definitely a big deal. Everybody's aware utilities that have been struck on open cut situations, like the examples I show on the right. Particularly of concern is gas lines or high powered electrical lines. Many jobs have been shut down when a gas line is struck. And there's a number of documented cases of explosions that are caused from those gas lines when disrupted and igniting. So utilities is definitely a high risk issue has to be dealt with. Okay, next slide. So how do we deal with them? Well, of course, the number one method is to have a good subsurface utility engineering program that starts during design and is continued on during construction. The subsurface utility programs, or SUs, we call them, will be able to come up and identify where there's lines that might not necessarily have been shown up on plans. They can also use a soft dig back truck, such as the one in this picture, to be able to find the top of that line so it can be shot and hard located in the field. And the beauty of this technology, which is that it's very unintrusive, and so the chances of disrupting any utility or is very small. In the old days, as many of the old timers know, we used to use backhoes to excavate that, and backhoes can be just as dangerous as trenching operations. So we've come a long way since that time. Okay, next slide, please. Okay, let's talk a little bit about the types of large diameter pipelines. Shao mentioned that this program is specifically talking about concrete and steel, but there's really four materials out there that are readily used for pipeline materials. Of course, the most popular and most widely used is steel. Concrete is highly used, and then in sizes under 64 inches, ductile iron is pretty well used, and especially in the smaller to mid-range. The real small lines, of course, are PVC. And then just fairly new to the market is fiberglass pipe, which can go up to 110 inches in size. Now, all of these pipes, with the exception of concrete, are considered a flexible pipe. And although you may not think of steel as being flexible, you'll certainly appreciate that as you see that hoisted if it's not restrained properly. It can flex quite a bit, as does ductile iron and fiberglass. And so the importance or the significance of that is that the flexible pipe rely on the subgrade or the pipe embedment for its structural strength. So once it's loaded from the soil overburden or any other loads that are on the surface, what prevents it from going out around is its ability to draw strength from its trench soil surrounding it. Whereas the concrete pipe is actually structurally designed to be able to withstand those loads in of itself and does not rely on the surrounding soil for support. Okay, next slide, please. Now, one of the things that is kind of unique about steel pipe is its ability to be customizable. It's the only pipe of the materials. The rest are more of the nature, if you want to forget the phrase, off-the-shelf products. They're cast, usually using molds or machinery that will put out certain sizes or certain pressure class of pipes. And so what you get, you have to order what you get. And so if one class doesn't work for you, you go to the next class. Whereas with steel, it's built to exact specifications that are provided by the engineer. The engineer calculates the pressure that the pipe needs to withstand and determines what thickness the pipe needs to be. Also, what kind of joints that we'll use, and I'll talk a little bit more about joints in a minute. The lining, based on what the application is, what the fluid you're going to be transporting in this case. The lining is, mortar line for water. That's most commonly used, but it's not entirely used. There are flexible linings that can be used on the interior. And then of course the coatings similar to the lining can be either rigid or flexible depending on what kind of interaction it would have with the surrounding soil. So all these things are specified by the engineer and then sent to the factory, and the factory manufactures the pipe based on those specifications. Okay, next slide. Okay, there are four basic joint types that are used, and the most common is the lap joint and the butt strap. And the butt strap, of course, the beauty of that is it has the ability to make up pieces that are irregular. So you can just you can cut pipe in the field and put two pipes together and then make a joint. Okay, next slide, please. Okay, with large diameter pipes, you're going to also have large diameter valves. Next slide. Okay, gate valves are the most common in water systems up to 24 inches, after which butterfly valves are used for economic reasons. This is a 108-inch butterfly valve weighing in at a whopping 40,600 pounds, not including the actuator, which weighs another 3,400 pounds. Next slide. The butterfly valve must be lowered by crane and matched to the 72 bolt holes on each flange for a total of 144 bolts to be set. At 20 tons, the worker is not maneuvering that valve. Next. As an alternative, butterfly valve assemblies can involve burying flanged pipes vertically, then bolting the valve, and then a second flanged pipe is then bolted onto the top of the valve. Next slide. The valve is then hoisted by the two flanged pipe and put into place. Next slide, please. The butterfly valve is then set in the valve vault, with the pipe being supported by the two reinforced concrete saddles. The men to the right are performing what's called a turn test to make sure that it takes just as many turns to open and close the valve as it did in the factory, which incidentally is about 405 to 414 turns. Okay, next. Now, not all valves under 24 inches are gate valves. This is an 84-inch gate valve. And so for a little bit of a trivia, let's see if you can guess how much this bad boy weighs. Okay, we're getting on everybody close. You're correct. It's correct. It's weighing in at 34.6 tons. So that is an awful lot of steel to be moving around. Okay, next slide. Okay, let's go ahead and talk about construction and inspection and testing for large diameter pipelines. Next slide. Okay, open cut is the most economical installation method. Production rates for large diameter pipelines vary and are typically much slower in urban areas than across country. This method of installation that you see in this slide is known as weld after backfill, which speeds up the production rate by allowing the pipe to be welded in the interior after it has already been backfilled. Next slide. Now, when receiving large diameter pipelines, you must make sure that it's properly handled and stored as to avoid any damage to the pipe. The pipe must be lifted using two slings to avoid any point loadings on the pipe. Likewise, it must also be stored properly using angle blocks to avoid that same point loading, which can deform the pipe and crack the lining. The pipe must also have end caps to be able to prevent mortar lining from drying out. Next slide. Each pipe has a unique number of, which is recorded. The lining is inspected for proper thickness and for cracking prior to installation. Next slide. The pipe needs to be properly bedded to make sure it's structurally supported material. The material here that's being used is concrete sand. The pipe also has stalls installed in the pipe at the factory to prevent the pipe from deflecting during transportation and installation. Next. Three basic types of shafts are used during tunneling. Tunneling is used whenever open cutting becomes unfeasible. The shaft to the right is a rectangular using soldier piles and sheet piling for soil conditions. When the soil conditions are a little better, we use circular shafts. The one in the middle is steel liner plate. And then the one on the right where the soils were the best, they use ring beam and wood lagging. Next. Okay, three types of TBMs are used to tunnel. The one on the left is a digger shield where the shield actually protects a live crew that excavates the tunnel and is pushed forward with jacking. The one in the middle is called a digger shield or TBM, open face TBM, which, having an open face. If you can see in the middle, it has a hydraulic arm which goes and digs and pulls the material back into the conveyor belt. And then the one on the right is what's referred to as a closed face TBM. And this particular one is a specialized closed face called an earth pressure balance machine, and it's used in areas of very poor soils. Okay, next slide. Okay, as the TBMs progress, they put tunnel liners behind them. There were three basic tunnel liners that are continuously used. One of the more popular ones is steel plate liners, which the individual steel plates are bolted together. The one in the middle, similar to the shaft, is consisting of ring beams and wood lagging. And then the one on the right is steel casing, which is jacked and welded into place. Next. Okay, of course, it's important, as we said, to inspect the pipe to make sure that everything is as it should be. On the right, we see a crew going through the pipe, measuring its deflection to make sure that the pipe is round, that there are no excessive cracks. And then the one in the middle is the welding. There's a certified weld inspector that will inspect every weld to make sure that it passes. And then on the left, they're performing a test called holiday testing to make sure that the outside lining is adhering to the steel and that there are no voids or pinholes. Next. Finally, once the pipe has been inspected and cleared, it needs to be filled, which process can take 2 or 3 days for the size of these pipes. They typically like to do it in sections rather than an entire pipe at a time. It's then chlorinated and then pressure tested before being put into service. And with that, I'll turn it back over to Shaw.
Thank you, Dennis. So this is going to be one of those rare few presentations that talks about pipeline asset management and condition assessment and not have a single picture of flooded roads and drowning people and vehicles. However, I do want to talk about how it's become so normal for us to turn on the evening news to see these pictures, these scenarios unfold before our eyes on major roadways where, there's been a huge flooding event because a transmission main has unfortunately collapsed. It has literally blown up and people and vehicles are now drowning. So in the past, I would say 2 decades, I think owners of transmission pipelines, these large diameter assets, have begun an organized approach to stay apprised of the condition of these assets to keep them at an acceptable level of reliability. This asset management approach is critical to maintain and support infrastructure networks. Sudden and catastrophic ruptures result in significant financial losses, damage to property, service disruptions to large numbers of downstream customers, and even worse, the actual loss of human life. The key is prioritizing repair and determining the most appropriate maintenance and repair technology based on both risk analysis as well as cost analysis. Oftentimes, what we see being done, especially by utilities who haven't had pipes blow up on them in the past, but all of a sudden had one, let's say a few months ago, they don't quite really know how to start up this, an effective, efficient asset management program for these large diameter pipelines. So my approach is to not only do the risk analysis, but also look at the cost analysis, because the technologies that are out there that provide solutions to extending the lives of these useful lives of these pipelines can vary quite a bit. The failure risk of a pipeline typically is expressed as the product of the likelihood of failure and the consequence of failure. The likelihood of failure is determined by finding the current condition of the pipeline through state-of-the-art condition assessment tools. It is then possible to decide whether a localized repair or a comprehensive repair should be employed. The goal is to forecast and subsequently prevent failure through selection of the appropriate rehabilitation. Most post-World War II large diameter pipeline infrastructure for water transmission were built primarily with prestressed concrete cylinder pipe, with more than 19,000 miles, as I mentioned earlier, manufactured between 1942 and 2006. However, the sudden catastrophic failure of PCCP, I think, was recorded as early as the mid-1950s and became much more noticeable in various systems around the country by the 1980s. In their 2006 AWWA Water Research Foundation study called The Failure of Prestressed Concrete Cylinder Pipe, Andy Romer and Dr. Graham Bell found that one rupture and 66 other failures occurred for every 50 miles of PCCP within 50 years of installation. The study listed 592 individual failures with details spanning 35 states and the District of Columbia. There are more than 20 reasons listed for these failures, including one that is widely understood by many in this industry that have dealt with this, the concept of hydrogen embrittlement of the pre-stressing wires. There are now many tools available for the assessment of existing buried pipeline assets. Using the data gathered from the use of these technologies, we can determine the likelihood of failures and prioritize repairs to stay within our limited infrastructure budgets. Before getting into a full-blown cost-prohibitive condition assessment program, a utility can do some desktop analysis, if you will, such as looking at a pipe's material, its age, diameter, and most importantly, any failure history. This can then be followed by above ground assessments, for example, such as soil corrosivity, electrical potential, stray current, correlator leak detection, and pressure monitoring. And then if these findings warrant it, then the next step can be the internal assessment of the pipeline to detect leaks and gas pockets, as well as visual and wall condition assessments. The most advanced condition assessment programs will typically include transient pressure monitoring, leak detection and finding air pockets in a line, and then employing electromagnetic inspections, which can yield the number of wires that may be broken within a given section of pipe. And on a more long-term basis, acoustic fiber optics, known in the industry as AFOs, AFO monitoring is a long-term solution and provides real-time data. It's a technology that can detect wire breaks within pre-stressed concrete cylinder pipes as they occur while the pipe is in service. Finally, let's take a look at some rehab options that are pretty, I think, universally accepted. I have taken the liberty to label each of these technologies by whether they're used as a localized repair. That is, they're used. These technologies are typically used when the consequence of a failure could be very high, which is usually the case in large diameter lines, or for a more comprehensive repair, which means that longer segments of the line involving more than just one or two joints, usually, a quarter mile, half mile or more, are rehabilitated. Again, you're looking at which technology should be employed based on the risk of the failure of your line. The price tag, as I mentioned earlier, on these technologies can vary substantially. So it's important to pick the method that meets the specific needs of the utility. Not naming any specific technology, I can tell you that amongst those that are shown here, on a per foot basis, one technology can be $7,500 per foot versus another that could be $1,300 per foot. So quite a bit of difference, and therefore I think it really warrants that we not only do the risk analysis, but also a very close cost analysis based on the type of technology that you're looking at employing. So let's look at the very first one, remove and replace. Now this is always an option, and I label that as both a comprehensive or a localized repair. At some utilities, if they identify, let's say, 4 or 5 sections that are badly in distress after a condition assessment run, they will typically go in, remove those 5, 6, 7, 10. I've seen up to over 70 sections being replaced, where the PCCP is just removed completely. And what I'm seeing more and more happening these days, especially out on the West Coast, is they replace them with steel pipe. That's almost become standard in the Western United States. Now in Central United States, out on the East Coast, I've seen PCCP sections being removed and then replaced with newer PCCP sections. So this is why I say that it's this can be a comprehensive as well as a localized repair. Another 2 other localized repair. One is the post-tension tendon repair, and the other one is CFRP, carbon fiber reinforced polymers. Those are considered localized repairs. Now, having said that, I have personally been involved in projects where we did several thousand feet of repair, because that is what made sense in that scenario with carbon fiber composites. So really it depends on a lot of different things. What value are you bringing the utility owner? Two technologies that sort of fall under comprehensive repair include steel cylinder-based relining and steel cylinder-based slip lining. And the difference between the two is that relining, you have a collapsible steel cylinder versus the slip lining where you're actually pushing in full round cylinders of steel pipe inside the hose pipe. Finally, under emerging technologies, one of the more common ones that I'm seeing more and more out there right now is a hybrid FRP system. That's called, I think, a strong pipe system, which is essentially a steel reinforced polymer system where high strength steel wire is sandwiched between longitudinal layers of glass FRP and a polymer matrix. In this slide, what I have done is sort of try to give you a comparison as you look at these different solutions. So, if you're the utility, if you're the owner, you're obviously going to look at the environmental impact, the social impact, traffic disruptions. How much of an inconvenience is the solution that you're going to select? How much of an inconvenience is that going to cause for your citizens? Other issues are obviously construction time. The longer it takes to put these things into place, the more costly it is, the more inconvenience it causes to others or in the vicinity of the construction. Also, 100-year service life. Is it realistic to assume that this particular technology that you're looking at, does it have, has it been around long enough for you to believe that it will last you 50 years or 75 years or 100 years, whichever it is that service life you choose? I've seen for these types of applications, I've seen a lot of utilities go with a 50-year design life is what a lot of them are pretty comfortable with. Two of these technologies I'm going to look at a little more closely in the next couple of slides are the two that are most widely used. First is the carbon fiber reinforced polymer, CFRP. In 2018, AWWA published a standard for CFRP renewal and strengthening of PCCP. It's based on an Lrfd design methodology, and it looks at a number of different aspects of the long-term service of this lining system. Which includes things such as, your internal working pressure, for example, internal working pressure plus transient pressure. What is going to be the result of the weight of the pipe and fluid on this lining system? Earth loads above the pipe, how will that affect the lining? What about live loads? I've seen a lot of these systems where even though they had no original plans of putting a road on top of a rehab that's being done right now, eventually a road comes on top of that. Now what? Well, you can retrofit it and make the pipe actually stronger by incorporating CFRP inside the pipe. So there's a lot of different parameters that are looked at in this Lrfd design process for carbon fiber. This slide kind of just walks you through the different stages. So, the main stages, you obviously go into the system, your PCCP line, you look at the existing condition, is there a lot of spalling concrete coming off the inside walls? Do you need to individually address those prior to putting on your layers of carbon fiber composite? A very important part of an effective CFRP system is the surface prep, where you have to hydroblast the inside surface of the PCCP. And if needed, you may need to make additional fixes to concrete portions that may have fallen off, that may need to be reinforced and fixed and patched prior to application of the carbon fiber. These systems are wet layup systems, where you put on layer after layer internally. So it's essentially a trenchless procedure. And one of the keys of the long-term success of CFRP is the joint completion. Very important to make sure that you terminate the joints properly, so that the water doesn't get in behind the liner once it's been put into place. The last thing we're going to look at is the steel relining. As you can see in this picture, this is a collapsed steel cylinder, which was first made and then cut longitudinally and then folded up and tied with these steel straps. You then start by removing 2 PCCP sections from your first portal through which you're going to enter the PCCP hose pipe. You transport the reliners into the hose pipe. Once they're in place, you cut the steel bands, and if you haven't experienced it, you should. If you ever get the opportunity, you should experience it. It's like a nuclear explosion inside the pipeline once the steel bands are cut and the cylinder actually opens back up. Once it's opened back up, it's fitted. They apply full penetration longitudinal seam welds and full fillet circumferential joint welds also. Once this is done, in the portal where the 2 PCCP sections were removed, they now replace that with 2 new pieces of steel pipe, put that within reinforced steel and concrete, and then fill the portal back up. One last thing that they do with these relining systems is they then go back in and actually apply a cement mortar lining on the inside. So with that, I just want to present a quick summary of the things that we have covered. We tried to keep this at a lower level. I recognize that there are a lot of 500 and 600 level experts watching this presentation. Really, this was meant more for people who may not know much about pipes at all. So we tried to cover a little bit about the history of large diameter transmission pipes, water pressure pipes, particularly steel and pre-stressed concrete cylinder pipes. Dennis talked about different design considerations, as well as construction and inspection topics. And then I looked a little bit at condition assessment of pre-stressed concrete cylinder pipes, how to assess your lines, and then to look at different technologies that are out there.